Welcome back. Well, a couple of things. First of all, I just want to look briefly at the scope, which is you get this on the screen properly. It's the Hanmatek 110 megahertz bandwidth scope made in China. Two channels, goes up to 110 megahertz, and I just got it delivered, and it's just going to say how good it is. It's a really nice scope, and I can vouch that it's a good scope and robust because I actually saw it being delivered as my car rolled into the property, or to the side of the property. The delivery guy was there, and he literally just flung the whole thing over the fence, like as if it was a football. So wasn't too happy about that, but the guy had gone by the time the thing happened, and I looked at it and examined it, and it's pretty good. So it's working fine. So it's a very robust machine. So I'm going to put some waveforms up it, and that's going to happen from an ESP32, which is programmed in C, C++ on the Arduino editor. It's going to be powering a motor. The motor's just freewheeling at the moment, doing nothing, so forget that for the moment. It's got one of these cheap H bridges, which is it's supposed to work up to about I don't know, 20 amps or something. I don't think it does, but they're quite good. It's more than enough for this tiny motor here. So the ESP32 goes into the H bridge when it's connected. I've disconnected it at the moment, and then that goes into the motor, and to control the speed of the motor, as it usually will happen, and you get a speed controller. And the set point, it's going to be open loop, is a quadrature detector, a quadrature encoder, which has two outputs, as you remember, an A and a B, which are at 90 degrees apart, and that way you know whether it's positive or negative. But in this case, I'm only going from 0 up to a maximum, and I'm going to put out pulse width modulation in my program of 8 bits at 1 kilohertz. So if it's 8 bits, it's 0 to 255 integers that it should be given out. You can check that very easily. This is just my power supply, which was from J-Car. This scope, by the way, was very cheap. I think it's $170 US for what you actually get. I admit it's no good if you're professional, you're working into very high frequencies, but for many people this is probably all you want to do. So let's just turn up the PWM and we'll have a look at the PWM. We could look at the there's a test waveforms, of course, as in any scope, and you set that up first, and then you have to adjust the probes. It comes with 2 probes, and make sure that the waveforms haven't got rounded edges. But I'm just going to just zoom out a bit. There we go. As I increase the turn this round more, I get a higher voltage. The average value of this waveform, which is PWM, is going to go from about 0, very close actually, more or less 0. That's 0 here on the scope. I've set that up to a maximum of I think it's about 3.8 volts or something like that. It says now on this scope, the way it comes, it doesn't default to showing you the frequency and the voltage. You have to sort of set that up through the measure button, as in instruction manual. But you can see that here it's 1 kilohertz it's measuring, and in 1 milliseconds period, and it says that the voltage peak to peak is 3.4 volts that it's giving out. In older scopes, of course, you had to actually physically measure them. It told you how many volts per division or centimeter, and the same with the time base, how many milliseconds or microseconds per division. Modern scopes, you don't have to do that, but in this particular one, you have to, as I say, set up the scales for that. So you want to do that, you go to measure, and then you've got to do add channel 1, and then down the left hand side you see these are the things you can get. I suppose you want it to display RMS. Well, then we use this button here, which is a multi-process button, and it should take the, oh, it's disappeared. let's go again, measure, and then add channel 1, and then down here, there we go, RMS, and I press the channel 1 button now, and RMS voltage should appear now. Oh yeah, I think it will appear in a second. Go back here to that. Now let's turn on the scope. Oh, why is it not triggering? Ah, there we go. Sorry about that. You just have to let it. Takes a bit of getting used to. So yeah, that's me down at a very low value of PWM, and then that's me at the maximum. And you can see I've now added, I presume that's, oh, there's nothing there at the moment. So the RMS voltage is 2.4 volts there, VR. I presume that's VR, I've just added that to the menu. So these things don't appear initially unless you add them in, just a warning. It does have other features like the frequency domain, I believe, and it's got a split screen, which I don't really need at the moment. One more thing, I can control this, of course, from my, I was going to say potentiometer, my quadrature encoder here, but I can also control it from the web. This is something we did in one of the earlier videos. I'm going to, I don't know how to get it all in the screen. Probably won't be able to see it all. You see there, I'm controlling it from the internet, at least through the network. I wouldn't say through the, from the general internet. There we go. So I'm not controlling it anymore from the quadrature encoder. I'm doing it from the web browser. Yeah, this slider switch, and this is an asynchronous web server which you come across in an earlier video. I don't claim to be an expert in asynchronous web servers, but from what I read about it, is that basic idea is that with a normal web server, when you change something, you nearly need to refresh it every time, and with the asynchronous ones, it automatically refreshes, so you can do these kind of control type actions without having to sort of refresh your browser, which you'd have to do perhaps in a normal, or getting it to reread things, rescan. So I can control from either. I'll set the web 1 to 0. I see this one's still on. They fight each other if you're not careful on the software. So I'll put that on and then the other one on. You can see that he'll just turn the other one on. It's yeah, they sort of add. I've just put them so they add together. It's not very that satisfactory, but it'll do for the moment. Now I'm going to connect it to the motor and just show you a few other things. So now I've connected disconnected from the scope probe because it's too small to get the probe on. I'd have to sort of solder some extra wires on to get everything on at the same time. Disconnected the scope probe and I've stuck the ESP output pulse width modulation into this H-bridge, and the H-bridge acts like an amplifier, and it gives us out pulse width modulation with more voltage. It's going to be 12 volts because it's a 12 volt motor, and it's going to give me more current as well. I can't drive it obviously from the ESP32 in case anybody's thinking. This power supply is from J-Carts. Not that cheap actually, but I bought it quite a few years ago. So let's just try turning the control here, and the motor obviously turns around to our maximum. So the maximum is 255. It's open loop controls, no feedback or anything. Let's go on the web browser and do the same thing. I'm just going to put it there. You can see it started. to zoom out a bit. Oh, I can't actually zoom out any more than that. I'll maybe get a bit of it. Let's put it at maximum. Oh, what happened? Oh, there we go. Should actually go to 255. I don't know why it's going to 245. It might be this other control. Let's just turn that down. Ah, there we go. Yeah, the quadrature encoder was fighting it. So I'll put that. Right, let's go back there. A little bit of dead zone there. You can see there's not a lot happening until that's pulse 86. Sorry, 86 out of 255. Some people ask what frequency should you use for a motor, a DC motor for PWM, and some people say, oh, you've got to use a high frequency. Other people say you've got to use a low frequency. Well, if you use a low frequency, you will hear it, just like you can here. You should hear a sort of whiny noise. If you hear that whiny noise. It's a 1 kilohertz PWM, but the advantage of a lower frequency is you get less dead zone. It seems. Well, I've sort of played around with these small motors, and if you operate at a low frequency, you get less dead zones. In other words, where it begins to just move. Of course, there could be other effects happening here because there's a gearbox in there as well. You shouldn't forget that. So there it is, DC motor speed control, working locally from a quadrature encoder and from an asynchronous web server. So the plan is to differentiate the output, so I'm measuring speed basically on this setup, but how to do it optimally. There's a number of ways you can do it. You can set up interrupts, and you can and count the number of pulses in a given time. That's not so accurate at low speeds as it is in high speeds. It's much more accurate. It can also lead to delays. So there's a number of people who have looked at optimal filtering methods, Kalman filters and so on, to do this, and I'm going to be looking at Wiener filters, and that'll be the next part of the talk. Will just be the theory of how we can get from a noisy signal, which is position, back to velocity. Of course, we can just differentiate it, but that gives you a lot of noise. So is there a better way to do it? Okay.